Hey everyone, and welcome back to another edition of the Data Idols and Data Science Festival Summer School. I'm Jess, the Community Director at the Data Science Festival, and part of the team that has helped to put this summer school together. Summer School is a new initiative that we've put together as a team, and it's designed to be watched two ways. So if you're watching it live, in a second, you'll see our Slack channel come up in the chat. Please join that and use it to chat with other attendees, chat with us. If you got questions, you can pop them in there as well, and hopefully someone from the community will be able to answer you. Watching it on playback, thank you for joining us, and hopefully you're looking through the sessions and choosing some more to watch. Before we get started today, we just wanted to say a massive thank you to our partners in making the summer school a success. They've put in loads of time to rehearsing these, putting together content and presenting them. So we are very, very grateful to every single one of these speakers and every single one of these partners for making this such a success. So today's session is Introduction to Deep Learning, and it's with our partners Royal Mail, who've been fantastic partners for the last few years with us. So thank you very much for supporting us. And it's with Paola and Louise. So hope you enjoy and hopefully see you at another event. Thanks very much.
Hi everyone, thanks for joining us today, and thank you to Data Idols for having us. My name is Louise. I'm joined by my colleague Paola, and we are data scientists at Royal Mail. And today we're going to talk to you about natural language processing, known as NLP, and deep learning. So let's dive right in. So what exactly is natural language processing? So it's essentially getting a machine to understand human language. And now human language is completely unstructured, it's complex, it's diverse. We have, many different languages, and even within a language, there's lots of different grammar and rules and syntax. And in spoken word, we have different accents and dialects and slang, and it's super complex. So basically getting a machine to understand our language and pull out insight from it and even generate it is a big challenge. Hence why we need deep learning. So what exactly is deep learning? So if we think about the human brain is essentially a neural network. And what we want to do is simulate the behavior of a human brain. So the human brain is very good at interpreting text and interpreting language and transforming language and learning and doing very clever things. So if we can replicate that, that's going to be really useful. And a neural network typically has hidden layers, and a shallow neural network, one layer, and deeper neural networks will have 3 or more layers. So it's much more complex and can do much more complex things. So if you haven't come across NLP, here's a taste of what we use it for. This is by no means everything. There's tens, hundreds, thousands of different applications of NLP. The very obvious ones are Google search, things like Alexa, translation services, if we're translating from English to Italian, for example. So we use it for all sorts of things. But what are we going to talk about today? Well, we're going to take you on a journey through NLP and deep learning. And obviously, we're not going to cover everything in an hour, but we're going to try and cover some key areas. And hopefully, there's a good overlap with another talk from our colleagues at Royal Mail on neural networks. So we're going to primarily focus on NLP and some basic text processing techniques. Do a little bit on shallow neural networks, and then dive into some more complex, deeper neural networks. So let's dive right into some basic pre-processing, and I'm going to move across to my notebook, and hopefully you can all see that. So I'm going to start with a string of text. So this is a review that I've pulled from Trustpilot for Royal Mail, so a lovely positive review. And this is actually quite a straightforward piece of text. So in NLP, we might have many large documents of text. Within a document, we might have many paragraphs, and within a paragraph, we might have many sentences, and within that sentence, we have lots of words. So we want to try and break this up and make it a bit more structured. So that's essentially what tokenization is. We want to break our long string down into smaller tokens of words. So we're going to start off with a package called NLTK, and Python has lots of useful NLP packages that we use, and I'm going to pick a few of them to play around with. So we're going to start with NLTK, and NLTK has a tokenizer called regexp tokenize, and we're going to apply this to our paragraph, and we're going to make sure it's lowercase, and we're also going to make sure we get rid of any punctuation. So let's apply that to our string and see what we get out. So you can see that we've gone from a long string of text into a list of tokens, so a list of individual words. So that's great. I'm just going to point out this word here. So this is a contraction of I would, and it might be useful for us to expand that, so we'll give that a go. And again, I'm going to use this very handy package here called contractions to do all the hard work for me, and it's just going to expand that out into 2 words for us. So let's give that a go. So we can see we've gone from I'd to I would, which may or may not be useful. And a lot of these things depends on how you're using it and what you're using it for. So it might be useful in the future. So the next step we're going to move on to is word normalization. And again, there's lots of different ways to do this. And 2 very common ways are stemming and lemmatization. And there's a bit of an overlap between these 2. And essentially what they do is reduce our words down to a root word. So for example, we might have singular and plural words that we want to just reduce down to the singular form, or we may have verb tenses that we want to just bring down to the infinitive. So the difference between stemming and lemmatization essentially is that stemming is very kind of straightforward. We chop off any prefix or suffixes, and then we're left with the stem, the root word. But occasionally it could be that this word isn't a valid word itself. Whereas lemmatization is slightly more accurate in that we make sure that the root that we're left with is a valid word. So maybe we can give these a go and see what they look like. Again, I'm going to use the NLTK package. And within this package, there's actually a few different stemmers that we can use. I'm going to use one called Snowball Stemmer because it's got a great name. And we can also set the language of this stemmer. So what we're going to do is we're going to apply it to our tokens up here and see what we get. And if we have a look at the first token above, so we had the word another, and you can see we've managed to chop off the end of this with our stemmer, and we're left with another. So it's not quite worked very well on that word. But you can see here, for example, needed, we've reduced down to need. And there are other words in there that you'll spot that haven't been transformed so well. So we have to be careful how we use this. And let's have a look at the lemmatizer. So again, we're going to use an NLTK function called WordNet lemmatizer. And we're going to apply that to our tokens as well. And again, you'll get different results. And looking at this, it looks like our lemmatizer hasn't dealt that well with some of our verbs. So needed, we're still left with needed, which isn't great. Ideally, we'd like to see that reduced down to need. So you'll get varying results with your lemmatizers and your stemmers. So it's worth exploring those and how you use them. So let's move on to this next step of removing stop words. So stop words are words that don't really add any meaning to the text. So they're sort of filler words, words like a, the, very sort of useless words, essentially. They don't really sort of help guide us towards meaning or any useful insight. And again, we're going to use a stock word dictionary from NLTK. And again, we can set our language. Maybe we can take a look at these so you can get a feel for what these look like. So we've got lots of very kind of small, that, his, no, very small short words. And actually you'll spot we've got quite a few contractions in there, which is interesting. But essentially, it's very useful for us to remove these. So let's filter these words from our list of tokens. And actually we can see which words we filtered out as well. So you can see we've got rid of these stop words, which look sensible. It looks like they're not going to really help us very much in terms of getting any insight or meaning behind our text. And it looks like they've been filtered out nicely from our tokens. So that's great. And often we might develop our own dictionary of stop words. So I've just added a couple here, but potentially we could add some very sort of domain specific words. So for example, maybe we see the words Royal Mail quite often, but we know our customers are talking to us about Royal Mail. So it's useful to get rid of those words. So yeah, so we can filter those out too. So those are some very basic text processing steps that we go through. So I'm going to move back to our slide and we'll carry on along our journey. So the next step is vectorization, and we're going to look at some count-based models. So vectorization. So what we want to do is basically convert our strings into numbers that a machine can do things with. So this is where we need count vectorization, and this is also known as the bag of words model. So what we have is, so we've got 3 documents here, and we want to look at these documents, look at all the words that we have in these documents and create essentially a bag of words. So all of the words that we see occurring in all of our documents. So for each document, we have a vector of counts of words in that document. So that's a good start. And you'll notice that the word royal and the word mail are very frequent. In fact, they occur in all of our documents. And as I mentioned before, they're not sort of adding much meaning to our text. If we consider this first document, great service from Royal Mail, essentially if we remove from Royal Mail, the core meaning behind that is that the customer is talking about our service and they're describing it as great. So that's kind of the key word. So maybe there's something that we can do. Can we apply a weighting to these words? And the answer is yes. And that's called TF-IDF. So this is term frequency inverse document frequency. So this is where there are words that have higher frequency throughout our documents. We want to give them less weighting, essentially, because they're less important. And then the inverse is true. Words that are sort of less frequent throughout our document, so there might be very high frequency in a single document, but less frequent overall, means that they're more important in that document, and maybe they represent more of the meaning or the sentiment behind that document. So let's give this a go in our notebook. So this time, let's have a look. I think I've made a data frame. Yeah, there we go. So we've got our 3 documents here. And before we dive into our vectorization, we're going to understand the term n-grams. So what are n-grams? So far we've broken down our text into individual word tokens, but it might be useful to include maybe 2 word phrases or 3 word phrases. So these are named n-grams. So bigrams, trigrams, 4 grams, 5 grams, and so on. So again, NLTK, we're going to use the n-grams function. And what I'm doing here is I'm just going to take my first document here, just going to make sure it's lower text, and I'm going to tokenize it, and I'm going to apply my n-grams function, just so we can see what what the n-grams look like. So very straightforward. You can see we've got great service from Royal Mail. So those are all of the pairs of n-grams that we see in our first document. So we can include those as features. So not just single word tokens, but also bigram tokens as well. So let's have a look at vectorization, including our n-grams. So this time we're going to use XLNet, which has a built-in count vectorizer. We won't worry too much about these arguments that we're going to pass. We're just going to pass the n-gram one there. So this is our n-gram range. So we can set it to 2, 3, 4, whatever we like. I'm going to leave it as 2. So let's define that. And now we're going to apply it to all of our text. And I'm also going to convert the output from this, which is a sparse matrix, into a data frame just to help us visualize what that output looks like. So each of our rows are our documents, and each of our columns are our feature words or n-grams. So we've got 18. And actually, let's get a list of those just so you can see that, yeah, we've got individual words and we've also got our bigrams in there as well. So that's great. And then we're going to apply our next transformation, so our TF-IDF transformation. So again, using XLNet. I'm not going to go into detail on the arguments we're passing here, but we'll apply that to our matrix that we created up here. And again, let's put the output in a data frame so we can see what that looks like. So you can see now, instead of our 1s and 0s, we've got some weighted values here. And again, our 3 rows for each of our documents and our columns for our features. And what we can do is we can put that in a list. So let's get a list of each of our features and the weightings for those. So you can see here that we have low to high at the bottom. So our lowest weighted feature is Royal Mail, which is good. As we said, we see Royal Mail in all of our documents, so it's very, very common, so it's not very useful. So we want to give it a lower weighting because it's less important to us. And then higher weightings for more important features, so that's good. So that's a really whirlwind tour of some text processing steps and some vectorization steps to get you started. And we're going to move on to the next part. So we're going to move on to word embedding. So up till now, we've vectorized our words and they've been completely isolated in vector space. They don't have any relationship with other words. But ideally, we want to understand how similar words are related. So we want to, in some way, embed them into our vector space in a way that similar words are grouped together. So as an example, in these diagrams, so in our male to female example, ideally, we'd like to see maybe man and woman are close together as concepts, and king and queen are close together in our vector space as concept. But also women and queen are likely to be close to each other, and man and king likely to be close together. And obviously, the more features that we have, the more complex this is going to get. And we're going to have this very sort of dense vector representation for our words. And there's lots of different ways that we can measure the similarity of two ways. And one popular way is cosine similarity. And we're going to come back to this a little bit later in our notebook. But essentially, that's how we calculate a value for the similarity between two words. So how do we do this? And this is where we move on to neural networks. And we're going to look at this example in particular. Oh, and I've jumped ahead too far. Let's jump back. So we're going to look at word to vec. So this is a model developed by Google. And it's a very shallow neural network. So it just has a single hidden layer. And there are two approaches within word to vec. And the first approach is known as continuous words. So here, our input layer are the kind of the context words around a word that we're trying to predict. And then our output is going to be our target word that we're trying to predict. And then the other approach is kind of the opposite way around. And this is called the skipgram approach. And this time we have a single input word and we're trying to predict the words around that. And this bottom sentence here just kind of gives you a good understanding of that process. So, for example, the green word that we're iterating over is our target, and we have this window of the words around it, our context words that we're trying to predict, or the inverse true for skipgram. So let's maybe dive into the skipgram approach and just talk through this and our inputs and outputs. So essentially our input layer is our vector representation of our input word, and our output is going to be a vector of probabilities for the context word, the word that's going to be next, or it's going to be near that word. And within this, we have this hidden layer of word embeddings, and this is the really sort of computationally hard part, because we can define a number of neurons that we're going to embed our sparse vectors into, and as our number of features grows, our matrix is going to grow. So say we've got 10,000 neurons, we multiply that by even a small number, 50 features, that's going to become very big very quickly. But let's give it a go. So I'm going to move back to our notebook again. And this time, we're going to use a bigger chunk of text. So I've taken the text from Wikipedia for the Royal Mail page. So it's a lot longer text than we've been dealing with. And we're going to do some of our initial cleaning steps. So we're going to remove some stop words. We're going to make sure everything's lowercase. We've got no numbers in there, and then we're going to tokenize everything. So let's have a look at that. So what we get here is a very long list of lists. And if I highlight one of these lists, so each list is a sentence, and you can see each of our sentences has been tokenized. So that's a good start. And what we're going to do is we're going to train our model. So this time we're going to use GenSim. So again, another popular package for NLP. And we're going to use our Word2Vec model. So we're going to apply this to our sentences that we've tokenized. We can also specify a dimensionality. So let's go for 100. We can also specify a window size, so we can optimize this if we like, but we'll go for that as a starter. So we trained our model, which is quick, it's great, very easy, very straightforward. So what we can do now is going back to this idea that I mentioned earlier around how we measure similarity between two words. So our model does that by calculating the cosine distance between two words. So we can output the value for any given set of two words. So let's give that a go. So I picked post and mail, and we should get a number output from that. So ideally, the closer our two words are in vector space, the closer this value should be to 1. So maybe I can, if I put in two identical words, ideally we should get a value of 1, very close to 1. So 0.30 is a little close, and maybe we can look at maybe the top 10 closest words to the word post. And so you can see here, we've got the word penny, new, company. I mean, it's not a great result. Some of these are vaguely similar, post, mail. But as a kind of a very quick go at training our model and a very quick output, it's not bad. It's not bad. It's a good starting baseline that we can then improve on. So it's very, very straightforward to implement that, implement a Word2Vec. And if we want, we can save our model and we can come back to it. We can continue training it, or we can apply it. So that's Word2Vec. But Word2Vec does have limitations, and a lot of these are around the inputs that we're using. If these are getting, long, if we get longer phrases that we're inputting, there's challenges around that. Our window size, if we use a very small window size, it's going to be faster to train our model. That can lead to very poor embeddings. And in some cases, you may have words that are very contrasting in meaning, such as the word good and the word bad. If your window is very small, you'll end up with actually very close embeddings, which isn't great. And obviously, the embeddings are very application dependent. So there's a few models that have improved on this. So just very, very briefly, there's a model called Fast Text, which is a Facebook model, which is sort of an enhanced skipgram model where we include some subword information. Or there's something called GLOVE, which I think is a Stanford-based model from the Stanford Research Group. So GLOVE, short for global vectors. So this is where we take into account the global stats. So it's kind of a combination of skipgram and some count-based methods. So it gives us a little bit of improvement in the accuracy of our models, but we still have a lot of limitations. And a lot of the limitations are due to the fact that we might have varying lengths of sentences that we're putting in, and we have lots of different problems. So these examples are good illustrations of those examples of those limitations. Sorry. So here we've got a slightly different application. So we're translating from English to French. So we might end up with what we call bottlenecking, where we have these spurious words, or we have some alignment issues where we don't have like a single one-to-one sort of relationship. So that causes us problems. Or we have problems, this example where we've got the word left occurring twice within our sentence. So I left my book on the left. So the first occurrence is our verb leave, I left my book. And the second occurrence, the meaning is more left, right, directionality. So they're two very different words. And actually we need to sort of consider the context of that word and when it's being used. And due to how we implement very shallow neural network models, how the embedding of the word is kind of done later rather than at the point of the word. And on that note, I'm going to hand over to Paola because she's going to go into that in a bit more detail. And she's going to dive into some, deep learning. So Paola, over to you.
So, as we've seen with Louise, traditional word embedding techniques provide fixed length vector representation, which leads to misalignment and spurious word issues. Also, the single vector constraints makes it difficult to properly pick up on the contextual meaning, especially in long sentences where, in fact, these models experience a drop in the accuracy. So, as we can see in the image here, the output of the first part of the modeling, which is the encoder, is packed into one single context vector, so a fixed and unique vector per sentence. So this will be what is going to be used in the decoder phase, which isn't properly great if there's a long sentence and there's a huge and difficult meaning to that. The attention mechanism allows the model to focus more attention to certain factors and word dependencies when we process our data. The core idea is that each step of the decoder uses direct connections to the encoder to focus on a particular part of the source sequence. So attention doesn't encode the whole input into one vector, but it will utilize a different vectors per each output token. And this helps us in quantifying the token interdependencies. So, for example, in here in the image, we can see that in the first token of the decoder, C1, we will use as input a vector of alpha. These alpha are called attention weights, and each alpha will refer a token from the input, and it will tell us how much the token from the output should pay attention to from the input token. So each word in the decoder will have an attention vector assigned. Say if we have the sentence, how was your day? And we want to translate it to the French version, the attention component of the network will map the important and relevant words from the input sentence and assign higher attention to the output words with similar context. For example, here, the attention weight factor per word will have 4 elements, as it is in the input sentence. So the first word in French will focus more attention in the first word in English, just because it's the direct translation. But the second word in French, for example, will focus more attention in the first and in the second word in English, but just because there's not direct translation. And so on for the other words. So let's see now two of the most famous models using attention mechanism, Bert and XLNet. One of the most recent and successful adaptations of attention is Bert, a pre-trained model by Google, which provides us a bidirectional representation of text by jointly accounting from left and right context of tokens. It has been trained using text coming from a book corpus, resulting in 800 million words, and English Wikipedia pages, resulting in more than 2,500 million words. The bidirectional nature from which Bert has been created resulted in a really big improvement compared to the state of art of that moment, which were the autoregressive models. You probably have seen LSTM models during the previous courses in Introduction to Neural Network. These are autoregressive models that can only learn unidirectional information. So as we can see in the picture, in the decoder, YT, let's say Y2, depends on the previous step of YT1, but there's no way around. So we can say that these models are missing bidirectional context. Bert instead Bert has been built to properly pick up the general context of the sentence, accounting for both left and right. So Y2 will account also for the fact and the dependence coming from Y3 and also the other words going forward. So as I mentioned, a key factor in Bert is that it can properly capture the context meaning in a sentence. So in a sentence like, one bird was flying below another bird, the two embeddings of the word bird will be different this time. Also, while autoregressive models read the text input sequentially, as I mentioned, this time the transformer reads the entire sequence of word at once, and thus is considered bidirectional. Another factor that made Bert great is the transformer. It is built out of many parallel iterations of attentions. That is why it's called multi-head attention block. We're gonna go back into it later. So for each attention iteration, Bert builds up a stacked encoded layers architecture, as we can see in the image. So here, this is the version Bert 12 that Google has pre-trained. It has 12 hidden layers for the neural network, and it converts each token by construction into a vector having 768 elements. So as we can see here, throughout 12 hidden layers, we can convert the single vector, the single token, into a vector with 768 elements. Each one of these elements already incorporates the attention information because it has already done, as we've seen earlier. So CLS and SAP are called special tokens automatically introduced in Bert to keep memory of the initial corpus structure. Taking as example the sentence, "My dog is cute, he likes playing." The very first step in Bert will be tokenization, as it has been done and introduced from Louise. And we can see the result from tokenization, for example, here in playing. So it has been reduced to the root and kept the suffix in order to understand what is really saying the sentence. Then for the training part, Bert uses the previously mentioned layers architecture with attention information incorporated, but it computes 3 different embeddings. So the first embedding is the token embedding procedure. And throughout each of these embeddings, we can get the meaning of the word, the context of the word. The second embedding instead specify which segment the sentence is from. So the word dog here, it will have its own embedding, but then will be another embedding which will tell us that this word, that this word belongs to the first sentence. And the third layer of embedding, it will be the position. That specify the position of words in the original document. So let's say the dog originally he is in the second position of the old document. So this visualization shows you one attention mechanism within Bert model. So as I mentioned, Bert actually learns multiple attention mechanisms because of the multi-headed attention. These, in fact, are called, each one of these mechanisms is called head, and it operates in parallel to one another. This parallel mechanism enables the model to capture a range of relationships between words, which is much broader than what it would be possible with a single attention mechanism. In the example here, we can see in dark blue which word the model should pay more attention to for each token computation. For example, for the token crawled, it will pay much more attention to the word turtle in order to pick up more the context, as you see here. Yeah. So how does Bert learn? Bert learns the context of the sentence, initializing 2 unsupervised tasks in each iteration. The first one is the masked language modeling. Let's pick up the sentence, I want some pasta, for example. Here it wants to predict the word pasta, but it will use 3 different procedures to do it. For 8% of the time, it will replace the word to predict pasta with a mask. So it will be trained over the sentence, I want some mask. The 10% of the time, the words to predict pasta will be replaced randomly. I want some blue. 10% of the remaining times, it will be kept as the same. I want some pasta. The other task to make the model learning is the next sentence prediction, which predicts whether one sentence follows another. So considering the example, I'm hungry, I want some pasta. For 50% of the time, it will learn that I want some pasta is the next sentence to I'm hungry. And for 50% of the time, it will replace the second sentence at random, and it will give a label of not next. These 2 unsupervised tasks will give the model more opportunity to properly learn on the context and the use of each word and sentence. At the end of these 2 tasks, the model will have the final tune weights for the output text prediction, and then we can fine tune with our own data. So as I mentioned, Bert uses a multi-head attention mechanism. This is a job running the attention mechanism several times in parallel. Each attention output, which is each one of these, is independent and finally concatenated. A different input configuration is used for each one of these attention heads to learn also the most hidden word patterns. So through this repeated composition of word embeddings, Bert is able to learn and to pick up on a very rich representation also of the deepest meaning of the sentence and the words. But Bert has a big limitation, which is the underlying assumption of independence between tokens. So let's consider a concrete example. New York is a city. Suppose that Bert select 2 tokens to predict New York. Because of the independence assumption and because of the masked procedure I introduced earlier, it will minimize the objecting function as visualized here. So since there's dependency, it doesn't need to conditionate on New York when we minimize the objecting function for new. And as you see, it will predict on new given is a city plus York given that is a city. So that also to remember is that 80% of the time we will mask the words to predict. So new will learn with a masked York, which isn't convenient, and the way around for York. So that is why we need, a new model has been created. This is XLNet. And I want to remember you that until now, we have talked about only 2 kind of language models, autoregressive, which are the LSTM, as I've mentioned earlier, and autoencoding, which is such as Bert. Each one of these a specific limitation that XLNet has been able to overcome. XLNet is an autoregressive language model which computes the probability of each token, conditioned on all permutation of word tokens in the sentence. It has been trained over 30 billion words. And we can refer to this model as a permutation language model because it considers all the possible permutation of word in the sentence, such that per token you will have seen many different variants of context. Going back to our example here, since it is different on the assumption of dependence as it was in Bert, York, when we minimize the function for York in XLNet, we will see also new, which is good because we are not taking out any context of meanings. So, for example, given the input sentence, Mark has dinner late. For the prediction of the token 3, let's say dinner, it will use 4 different permutations. So in the first permutation, the token to predict it will be in the first place. In the second permutation, it will be in the third place, and so on. Since its autoregressive nature, we'll consider only the tokens before the token 3, but not in the original sentence, but in its permutations. So in the permutation 3, for example, the model will learn from the tokens coming before the token number 3. So from has and from late. And that is a representation of how the model will learn for the token 3 in permutation 2. So since each word, as you see here, we'll see all the possible context, the word dependencies will be deeply captured. In this model, there's also an intense and essential use of attention, because to save all the info of the original context, which is now shuffled because of the permutation, the model uses a 2-stream self-attention mechanism, as in layers during the pre-training. Each token, let's say here X, has 2 associated vectors that we can think of it as 2 hidden layers, so H and G. The H vector belongs to the content streams, and it represents the token embeddings as it was in Bert. And in the G vector belongs to the query stream, and it represents the positional embedding, again, as it was in Bert. This use of autoregressive behavior and attention made XLNet the state of art on NLP for a while, for a long time. So summarizing, we walked you through a long journey in NLP, and from the very basic pre-processing techniques for text, as in tokenization, stop words cleaning, and word normalization. Then we have introduced you with some basic models to process text data, such as count-based model, TF, IDF, and then some of the neural network models based on embedding techniques. Finally, to show how all these models can be improved, we have talked about attention and the two most famous pre-trained models using Bert and XLNet. So we want to leave you citing some references that we have used in this presentation and some further readings that we recommend. So please feel free to use them in order to know more about this field. So I'd say thanks for listening and keep learning, please.
Thank you.